In this video, we're going to transform a curve from polar coordinates to Cartesian coordinates and go back and forth. So rather than go and convert a point, we're going to convert an entire curve now. And again, where we're starting with are all of our transformation equations, where we take coordinates from polar and put them over into Cartesian or vice versa. So we had the following four equations. R is equal to plus or minus x squared plus y squared, and theta is equal to the arctangent of y over x. And we also had that x is equal to r cosine theta and y is equal to r sine theta. And big picture idea, we got all of these coordinate transformation equations coming straight from what we know about right triangles, using trigonometric identities or relationships as well as Pythagorean theorem. So let's start converting entire curves from different coordinate systems. So the first example we'll do is convert Cartesian curves to polar. So example number 1. We're starting off with y equals 8x squared, and we want to convert this to a polar curve. And where we're going to be finished is when there are only r's and thetas left. So how can we go about and start this conversion process? Well, we're going to use everything we know from the above transformations. For example, we know that, well, x is equal to r cosine, and we know that y is equal to r sine. So we could go ahead and just start plugging in what we know. So if y is equal to r sine theta, and x is equal to r cosine theta, let's just plug in those things. So we have y is equal to r sine theta, and we're told that, well, x is equal r cosine, so x squared would be r squared cosine squared, and therefore now we have that relationship. If we wanted to, we could try to simplify a bit. And we get that, well, we can cancel out a factor of r. And we have, I guess, 8r cosine squared equals sine. And at this junction, we've eliminated all the x's and y's, and we only have a relationship between r's and thetas, and that is our polar curve. If we wanted to, we could try to take it one step further and actually just go ahead and solve for r. So in this case, r is equal to 1 over 8 times sine of theta all over cosine squared of theta. All right, let's do another example. Converting, this time let's go y squared equals x squared. And again, we just take what we know from those transformation equations. We know r is equal to r sine theta, so y squared is equal to r squared sine squared. Plugging in what we know for x, well, x squared is equal to r squared cosine squared theta. So we actually have here now is a curve in which sine squared theta equals cosine squared theta. In other words, we have a curve in which we have tangent squared theta is equal to 1. And I should say before we start canceling r's from both sides, like we did in this example, or the previous example for that matter, we're assuming that r, of course, is not equal to 0. But again, we're ending with equations in which there are no more x and y's, and we only have r's or thetas left. Let's do another example. This time, let's convert from polar curves to Cartesian curves. So we're going to be starting off with a curve written in r and thetas for polar, and we're going to end with Cartesian curves where there are only x's and y's left. So let's do a couple examples. The first example, we'll start off with a polar curve. R equals 3 cosine squared theta. Well, in this case, let's just write down all of those transformation equations we have. So again, the transformation equations we have at our disposal is r equals plus or minus the square root of x squared plus y squared. We have theta is equal to the arctangent of y over x. We have x is equal to r cosine theta, and we have that y is equal to r sine theta. So what can we try to do here? Well, we have this cosine squared term, and we also see, well, if we have a cosine term, we could try to weasel an x out of it as long as we have r's on top of those cosines. So our first move, let's multiply both sides by an r squared. So we get an r squared times cosine squared. So on the left side, what that means is we will have r times an r squared. The right side will have 3 times r squared cosine squared. And now this entire r squared cosine squared, well, that'll just become an x for us, or sorry, an x squared. In the left-hand side, we have an r cubed equals 3x squared now. And while in this x cubed, or this r cubed term, we know what r is. R is equal to plus or minus that square root, so we can just go ahead and cube that. So we have that r cubed is equal to plus or minus the square root of x squared plus y squared. That quantity cubed equals 3x squared. And at this junction, there are no more r's or thetas anywhere, so we do have a Cartesian relationship now, or a Cartesian curve. We only have x's and y's left. And the tricks in which we will use, or I shouldn't say tricks, but what we're trying to do is build again towards, like in this case, getting x's where we have cosines. Just multiplying those cosines by factors of r will allow us to rewrite them as x's. Or if we had sines, multiplying by factors of r, or making sure that we have r's attached to each sine term, will allow us to transform our sine into a y. So these will be the type of methods we go ahead and do. Converting cosines into x's, converting sines into y's, as long as there's the appropriate polar radius r attached to those trig functions.